Okay. All right. My bring my owl today. But hopefully the folks can still hear me through the normal mic. Share my screen. Okay. Let's see if I can do this. Just mirroring it, right? Yep. Yep. Okay. Stop sharing. Let me reshare. So two. Okay. All right. Let's start with a quiz. So I've been asking you to read this paper for a while now. Now let's take a quiz on the paper. Okay, so we're going to do the same thing we did last time. So please use your phones and try and capture that QR code. Um, can you raise your hand if you were able to get in? Yes, some folks did. Okay, good. All right. If there's a problem, let me know. Just raise your hand, but hopefully it should be easy enough to log in. Most of them are just true false questions. If you read the paper, understood at least a little bit, hopefully it's not that hard. Again, this is bonus, so just do your best. Responses starting to trickle in. 3 of you are done. Rats. We had 6 complete. A couple more minutes. If you read it, either you remember it or you don't. Start wrapping up. Remember, this is low stakes. I'm not going to judge you if you don't do well. Maybe I will. I will assume you didn't read the paper if you don't do well. That's what I will do. So we've got 20 responses in. Nobody's got 100 yet. There's no bug in any of the answers. There could be. I wrote this quickly, so we'll go through them. So 25 people in person, 26 responses. The folks on Zoom, how many do we have? 12. It's unclear if they're all answering. Can you please raise your hand if you're in person and you are not done? Everyone here is done? You in the back on the phone? The guy behind you? You done? You're done too? Everyone here is done? Okay. All right. I think I can like make it. I'm gonna shut it down now. I think I can have it stop recording responses. And then we can all look at how this went. How do I? Okay, there we go. Accepting responses. All right. If you haven't submitted it online, I'm going to turn it off in 5, 4, 3, 2, 1. All right, 35 responses. Let's take a look at how things went. Okay. So chance is 50-ish. Module of one question. So let's say that question's out. So chance is like 40, I guess, if we assume that, you know, that one question wasn't 50-50 and was impossible, let's say. So you did, the average is definitely better than chance. Median's, you know, better than chance-ish. And we had some scores around Maggie. Okay, the worst question was the first one, actually. And this is kind of a subtle, okay, let me just quickly skip the scores and then, nah. Sorry if I de-blinded you. Okay, so this first question, most people got it wrong, actually. Why is it wrong? Yeah. It's a device from the host, right? cuDNN is a host library, right? This is not something that you plug into your CUDA kernels. This is meant to like remove people from ever having to write their own CUDA kernel. So somebody in the CPU who knows that they want to do a convolution, right? Like you're plugging it into the cafe back. Who's heard of cafe? This thing that they talked about. It was like an early version of, it was one of the earliest versions of a machine learning DSL or framework, if you will, to like help people to specify people networks. You know, it's meant for people who are designing these frameworks to plug their sort of high-level interface into a CPU-based function, and then it will call the GPU functions for you. It's not like, it's not meant to give to you guys who are trying to write a CUDA kernel, right? This is like at a higher level. So that's why that one, it's not device functions, they'd be global functions that you would call into, like they're big kernels, not individual functions. Second question, the data layout of cuDNN is fixed and integrated, and integrating into other frameworks like Cafe requires a translation layer, and the answer there is false, right? That thing was sort of explicit. If you read the paper, right, it's explicitly designed to allow different frameworks to represent data however they like. So that way there's not this translation overhead. That was one of the sort of key design points here. Because sometimes there's all these dimensions, right? Like all this alphabet soup of convolutions, the frameworks may choose to lay things out in different orders based on just what their design decisions are. And this framework, they didn't want to tie people to a particular configuration of the data in memory. So you have an interface to specify what the configuration of your data is in memory, so you can plug into different interfaces easier. Okay. Okay. Perform convolutions, cuDNN performs gems by transforming input matrices into tuplets in the GPU's global memory. This is a hotly contested question, but still, like one more person that not got it right at false. Why is this wrong? Not you this time. Somebody else. Why is this statement wrong? Is it wrong that cuDNN performs convolution using gems? Yes or no? No, it's not wrong. That's a correct statement. That's what the paper basically says. This is like a 9-page paper. Like this is the first implementation of cuDNN. It's gotten a lot more complicated as sort of things have evolved. But that was sort of their shtick, right? Is that I want to use gems to implement these convolutions. And if you look at the data, some of those other frameworks can do better as the batch size gets bigger, right? Because they're not using gems, they're using true convolutions. Sometimes you can do better with it. But the key part here is in GPU's global memory, right? The problem with doing this tuplet thing in a very naive way is, you know, you have your convolution and then you turn it into a matrix with the tuplets transformation. But that's a huge amount of memory, right? And memory capacity on GPUs is precious. It's very like HBM by its very nature is high bandwidth but low capacity. You cannot build terabytes worth of HBM and put it on a GPU. It's just, there's two things do not mix together in current implementation technology. So the max memory capacity on GPUs even today is like order of 100 gigabytes. That's it, which is drastically less than what we can get on CPUs. Terabytes worth of memory on CPUs. So you cannot do this transformation in global memory because you'll suck up a bunch of global memory for this essentially intermediate matrix. So what do they do instead? On-chip memory. What do you think they mean by on-chip memory? Caches, somebody said, shared memory. What else? They didn't explicitly mention it yet. Texture cache. What else? What else is on chip that is a memory? Registers. Okay. Like they manage the register state also. Like it was, because if you think about how Core is designed, it's got a whole bunch of registers and it's got a whole bunch of shared memory. If you're really a ninja, right, you need to soak up as much of that on-chip storage as possible. So you have to craft your kernel to both use as much shared memory as possible and use all of that register capacity as effectively as possible. And that's what the guts of these optimized kernels that they implement will do. They will try to use up, basically capture as much locality like in core on chip through all of the different storage structures that are available to them, which is a non-trivial task, and it changes every generation, which is part of the reason why they sort of released this library. Okay, so this one, actually the majority got both of the correct answers correct, right? Like using gems for performing convolutions is preferred because matrix multiplication obviously is highly optimized. If you have a good optimized implementation, you can get a high compute density if your matrix is big. In-memory capacity efficient, it's not memory capacity efficient. You are by nature creating redundancy, right, when you do the toplets, and it's not good for memory efficiency. So you have to play these games of like, constructing the toplets on the fly in the on-chip memory. Maybe that one is a little bit confusing, but I think I don't know what we meant by memory capacity was global memory capacity generally. The performance of convolutions as jams is relatively stable, meaning that as you change the batch size, for instance, the tops remains relatively stable, and that's true, right? Because you can get more optimal implementations of different convolutions depending on the stride size, depending on the size of all of the various dimensions by doing like a pure convolution kernel, but it varies widely, okay, depending on the size of the matrices. One nice thing about matrix multiplication is that what matters is actually the product, right, of the two inputs, not the individual size of each input. So as you go through most neural nets, and it says this explicitly in the paper, oh, maybe I didn't actually put a right answer for this next one, which was, oh my God, right. If you go through neural nets, like it says in the paper, in the beginning, the channel size is relatively low, right? And then as you keep going, the channel size blows up. But then the sort of product of the channel and the rest of the dimensions sort of remains relatively constant. So the raw performance as you move through the network starts to get better. Okay, this one, I will fix it in post, but what do you think the right is? So FFTs are inefficient for performing convolutions with a step size greater than 1. Most people said true, a collection of people said false. So true is correct. So most of you got this correct. There's probably a couple hundreds in there because this was basically not counting anyone as 10 points. Why is that? Who remembers the paper can tell me why that is? You remember? Yeah.
Because when the stride is greater than 1, you're performing less computation, so it's faster to perform dense computation and then subset. Exactly.
So if the step size is 1, then you're sort of moving individually. The window goes one by one across the input, right? If the step size is greater than 1, you're effectively skipping stuff. And when you do the transformation to put the FFT into the frequency domain, you're transforming the whole thing. And you actually have more sparsity, right, than your transformation is allowing for. So if you have a big step size, you're doing way too much work to perform the transformation into the spectral domain. And then it's complicated to do like a right, transformation from into the frequency domain. And then then the alternative is you do subsampling, but then that gets more complicated. So typically FFTs are not a win unless the step size is very small. That's the claim of the paper. And in this early version of cuDNN, they just didn't do them. Okay, everything was just done using gems. Today, there are some sizes where this makes sense and step sizes where this makes sense. And cuDNN will have heuristics to pick which one it'll perform. Okay, because sometimes it is better to do the FFT, but the claim in this paper, at least, was that it was not good in general. Okay, performing direct convolutions can be better performance than gems, but it's far less stable given different sizing of the center of the loop. Most of you got this right. If you just looked at the data graph in the paper, you'd be able to sort of get this one right. That is generally a true statement. The gem implementation of convolution described in cuDNN requires more floating point math than the normal gem. The answer here is false. Why is that? Yeah.
They traded off with
more integer math, right? So if you're doing this tricky thing where you are keeping the matrix in its raw convolution form in global memory and then loading it down into your on-chip storage, you need to do a bunch of index magic, right? Essentially, that's like, I need to pick the pieces of this thing in global memory that I need and then pull it into my on-chip storage. That's a whole bunch of extra computation to figure out where that index is, but none of that's floating point, right? The floating point is the math of doing the gem, which doesn't change, given the same gem size, right? So what does explode is the number of integer computations, because now you have to do all this indexing to figure out what piece of the matrix to load into your on-chip scratch pad. And most of you also got this right, at roughly the same rate as the other question. And the final one is, oh no, wait, this is another one. In the paper, cuDNN's matrix performance is better than competitors across all batch sizes. Okay, so 14 of you didn't even read the data graph. Right, there's literally a graph in here that's like, it's just cuDNN. Performance versus batch size, and cuDNN's kind of flat, right? At low batch sizes, it does pretty well. And then the other frameworks, one of them is just complete crap, right? Which one is complete crap in this paper? There were 3 frameworks that they looked at. What were they? cuDNN, CompNet, and I mentioned it already, Café. Yeah. Which was the worst one? Café. Café was just universally bad, right? Because it was kind of not a great implementation. It was one of these early things hacked together by people who weren't necessarily GPU experts, and so it didn't do very well. So cuDNN had always overperformed it in the data. But CompNet actually got better as the batch size got bigger because they were doing true convolutions instead of gems, and they could find some more efficiency. And I'll also point out that all of this is pre-tensor core. Okay, all of the machines that they did this on are they are Keplers and Maxwell's, which is before the tensor cores, which were introduced in Volta about 4 years after this. So the performance of gems in general got way better once tensor cores got introduced. So then there's this extra bump that made matrix multiplication even more of a desirable option versus what this paper is showing. In this paper, they're just doing all of the matrix multiplications using fuse multiply adds in traditional SIMT pipeline, okay, which is what you do if you don't have tensor cores. So again, the fact that they were sort of building everything down to matrices 4 years before they released a part that had a matrix multiplication unit on it is sort of indicative of the way they were thinking about trying to optimize these things for machine learning. Focus everything towards gems and then make gems better and better as you can. One person said false. Okay. So the last one is the paper describes the very first implementation of cuDNN, but the framework has evolved significantly and in interesting ways. I couldn't have led you to this answer with any more text. Maybe somebody's just guessing randomly to get it over with. Yes, this is true. So you can go look at the website. There's a cuDNN website. There's full documentation. You can pull this down. You can play with it on the GPUs even that you've got access to in this class. I think they have cuDNN installed. So you can look at the APIs, you can pull down some examples, and you can play with them to try to see how cuDNN does on convolutions of given sizes. Okay. And I'd say it's relatively easy to use. Like if I see some people smiling, if you've got your head wrapped around convolutions in the first place, then cuDNN is pretty intuitive because you're just defining, you're basically pointing it at the the data types. I mean, it's that same 7-nested loop that I showed you in class. That's exactly what's pictured in the paper. And all of that terminology is sort of bled throughout the cuDNN library. So like I said, this has evolved a lot, of late, but it sort of has provided this stable interface to all of these frameworks so they can call this optimized library, and then NVIDIA can sort of ship their secret sauce of how we're optimizing your particular machine learning needs today, and nobody has to worry about, even the framework developers don't have to worry about writing CUDA kernels, right? Like it takes away the need for these folks to have to write CUDA kernels, which really, to peak performance, takes a lot of knowledge about how the hardware works. Any questions on this? Okay. This was an easy read, I hope, right? This is like an 8-page archive paper written from industry with a very directed approach. And the reason to get you to read this is just to give you a sense of, how cuDNN started. And who's heard of cuDNN before this class? Only a subset of people. Okay. So, this sort of remains the standard backend for implementing most machine learning layers. This and cuBLAS, which is the linear algebra library. Questions before we move on? All right, good. Let's go back to our stuff on microarchitecture. Go down here. All right, so we finished off last lecture talking about this sort of two-loop approximation, or this two-scheduler microarchitecture of the GPU core, where we've essentially got a decoupled front end and back end. This, again, if you look at this, it's sort of similar to CPU design, right? Because you've got this decoupled front end that's doing fetch and putting stuff into the ROB and filling up the issue queue. And then you've got this back end issuing mechanism that's picking up dependencies and issuing stuff that's independent in an out of order manner. The implementation of the GPU is similar, except we're not going to do anything out of order, because out of order is super expensive to implement. A lot of TCAM lookups, and we hopefully should have enough parallelism among warps to not need to extract ILP within warps. We sort of went over the big pieces here, right? So you go through fetch, iCache, decode, you put it into something called an iBuffer, which is just like a temporary holding space that has the decoded instructions. And it will interface with a scoreboard that's sort of keeping track of all the dependencies, okay, and all of the warps and all the instructions that could potentially be in flight, because we don't want to violate any dependencies in the instruction and create hazards in the pipeline. And so the issue scheduler is tasked with doing that. Our friend, the SMT stack, okay, this thing that's keeping track of the divergence in each warp, this also lives here, which is given to the issue scheduler, so that way it knows, what mask should be passed to the SIMD pipeline when you execute each instruction. And then we also have the SMT stack being fed by this predicate. Okay, so why is there this backwards predicate thing coming from the operand collector? Well, because if the instructions are predicated, okay, remember we can do branches either by true branching with the SMT stack, or we can have predicate registers. Then the instructions will need to read from these predicate registers. It'll apply on top of whatever mask is on the top of the SMT stack, and then those instructions, it will tell you then what lanes to execute with. There's this blob in here that I'm calling the operand collector right now, which you can think of as the register file. We'll talk about precisely what that means, hopefully this lecture. And then of course it issues down into different SIMD data paths. I'm simplifying the design here, where we've just got one ALU path and the memory unit. In a real GPU, we would also have tensor cores, we would also have special function units, we would have a separate unit for integer operations, etc. And we'd have multiple pipelines that you can issue into. Sort of a standard, multiple issue or multiple pipeline design of an in-order processor that's highly multi-threaded. Okay. Questions on this? Does everything in this diagram make sense to you guys so far? If you've taken any basic architecture class, no confusions, no questions? Yeah. No?
Anyway, yeah, with the iCache, yeah, with the iCache, ever have this all beyond cache miss?
So what will usually happen if there's good instruction locality is that the front end will go very fast, right? Like if you have all these warps executing, all start at the same place, they're all running the same program. So warps are going to prefetch for each other essentially in the iCache. And if your instruction footprint is pretty small, you're going to, and they actually preload the iCache with the whole program if it fits. The iCaches are actually pretty big these days on GPUs, 128K at the L1 level. Some of the programs just fit completely in the iCache. So what will happen is the fetch scheduler will go like, hopefully hit in the iCache, which will mean it will just fill out the instruction buffers. And then it will just be stalled on a structural hazard because there's no room in the iBuffer because the backend hasn't caught up yet. And then as the backend depletes the iBuffers, the fetch scheduler will just follow it because it'll see a new hole and then it'll fill it. And so usually that's the way that this will operate. So you'll either be stalled because of an iCache miss, or because there's a structural hazard because you don't have a new iBuffer spot to fill, or potentially there's a control hazard, meaning there's a branch in flight and you're waiting for that branch to resolve before you continue. Okay. Other questions? Okay. All right. So at a lower level, how could this be implemented? So this is the front end, sort of zooming in. So what we'll have is basically a bunch of PCs that are going to go to the iCache, and we're going to select which of those PCs we're going to use, and each of the PCs corresponds to a warp. Okay, so at the hardware level, at this level, we don't actually care about thread blocks. All we know is that we've got these thread blocks assigned. These thread blocks contain warps, and then all of these warps are valid to issue, okay, or valid to fetch from. Now you can play games with, okay, I want to prioritize between a thread block, but at the hardware level, you're just giving it threads. And if you have, if you had 64 warps that all came from 2 thread blocks or 64 warps that came from 8 thread blocks, it doesn't really matter at this level. They're all just sitting there waiting to fetch, okay? So you've got PCs associated with every warp. There's some arbiter here, which is just a simple selector, where you'd have some algorithm to figure out, okay, which PC am I going to send to the iCache in this particular cycle? The iBuffer contains the decoded instruction. It'll have a valid bit to say whether or not it's actually been fetched yet, right? This is a hardware structure, so you need valid bits. And then it's got a ready bit that the scoreboard will write to when it's ready to actually be issued. So this instruction buffer serves as the sort of, the go-between between the front end of the pipeline and the back end of the pipeline. The V bit gets set by the front end and the R bit gets set by the back end as things, mark off that this instruction is ready. You can have more than one instruction in the iBuffer for each warp. In this example, I'm showing just one instruction per warp, but the instructions could have, 2, 4, 8 instructions per warp. And as long as they can be issued in order, back to back, that is an allowable schedule. Okay, it won't issue them out of order, but if, for example, we had a bunch of, what a compiler will often do is something called load hoisting. Who's heard of this before? Any compiler people? Have you heard of this term load hoisting? No? Who's taking a compiler class at Purdue? They never talked about load hoisting? Okay. So let's say I compile my code and I've got load add, load add. Okay, maybe it's just the terminology you guys don't know, right? Okay, so if my code got compiled like this, then there's a load use dependency here, right? And then there's a load use dependency here, assuming that these are the read registers on the add instruction, okay? How can I optimize this as the compiler? What can the compiler do here? No thoughts? This is bad, right? Load use is bad.
Put instructions between the loading.
Yeah, what instructions I put there?
Independent.
The load instruction. Okay, that's load hoisting. And so what most programs look like, especially GPU programs, if you just unroll the loop a bazillion times, like imagine that this is inside a loop, right? There's some target here, and then there's a branch at the end, and maybe there's a whole bunch of these things, right? What you'd want to do, you're going to have like 50 of these load use things right away. And so what the compiler will do, and if you look at any compiled GPU program after it's done the final optimizations, it will put all the loads up top. So you'll start out with like, 20 or 30 global load instructions right at the beginning of every warp, to essentially just like go soak up all the memory bandwidth as much as you can and keep issuing instructions to fill up the register file state, essentially, so then you can go do all of your adds afterwards. Okay, so this is what's commonly referred to as load hoisting, where you're sort of taking loads and sort of moving them up to the top beyond the independent instructions, so that way you can create more space between load and use. And it's a super common optimization that happens in GPU programs, especially with unrolled loops. So if I have, why I went down this road is to sort of explain to you why you might want more than one entry in each of these I buffers for each warp, because if I could fill 4 loads in there, then I could issue the 4 loads back to back, right? And with no dependency issues because they're all independent instructions, okay? Now, if I had this and I had 4 entries in my I buffer, there's still nothing I can do, because as soon as I hit this add instruction, I hit a true data dependency. So I'm not going to issue out of order. I have to wait, and that's bad. So the compiler plays a very critical role in essentially creating ILP, from the code as much as it can, okay? Questions on this? Make sense? Yeah. Yeah, good question. That'll happen in the back end. So at this point, we don't know what the extent of the coalescing is because we don't have any addresses. Right now, all we have is just program counters. Yeah. So, and yeah, makes sense. Other questions here? Yeah.
The instruction like leaves like after it's done execution or after?
Yeah, that's a good question. Does it leave the I buffer after issue or after execute? There's different ways you could design this. If you need to replay the instruction, which is a mechanism we'll talk a little bit about, you're better off not vacating it from the I buffer, in which case your I buffer entry gets consumed until it's completed. You could delete it on completion because everything is in order. It's okay. You know that there's no structural hazards when you issue it. Or sorry, you could, delete it not on completion, but on issue. And then you would get more room in the front end. And which one it does is really a design decision on how the core is built. But you have to be careful if you're going to delete it after issue. Okay. It's generally simpler to delete it after completion. Because, you can do things like replay instructions easier, et cetera. But that's a good question. Other questions? Okay. Okay. So issue. So this column here in the instruction buffer is basically got a ready or valid bit for every one of warps to say whether or not that warp can be issued in this particular cycle. And the scoreboard is nominally writing to this, right? It's writing to it when it knows that the instruction completed, and then it can sort of update that field to tell the issue scheduler that this thing is good to go. So if an instruction has a valid ready bit and a valid bit and a valid ready bit, if they're both set to 1, then the instruction can be issued. And then this algorithm, you can do many different things, because oftentimes in GPUs, more than one warp will be ready to issue on any given cycle. Okay, even more so than in CPUs, because you have all of this independent work. You have 64 different ways you can go in any given cycle. And so there needs to be some kind of heuristic to pick between all of the warps that are now ready to issue. And there's different algorithms that have been proposed in the past, and there's different algorithms that are used in real hardware. In fact, there's some evidence that actually shift the scheduling algorithm based on the demands of the workload, because it can matter quite a bit. One option is something called greedy then oldest, meaning that you just keep issuing from the same warp until you can't issue from it anymore. And then you sort of defer to the oldest warps, which will end up making progress sort of with the older warps faster than the younger warps. So you get this kind of skew in where they're at in the program, which is an unfair schedule. There's something called a loose round robin schedule, which is round robin, as you would think, but it's loose because if you basically give every warp a chance to issue. Okay, so you start with warp 0 and you're like, okay, can you issue? If you can issue, you let it. You move to warp 1, you say, can warp 1 issue on the next cycle? If it can't issue, then a strict round robin scheduler would then say, I'm going to wait until 1 can issue, right? That's a strict round robin. But a loose round robin says, okay, if 1 can't issue, then I'll move to 2. So you sort of lose your chance, right? If you're not ready to issue when your chance comes up. That's what the loose round robin does. And then there's several different variants of like a hierarchical or multi-level scheduler. We'll take a look at a couple papers that have proposed something in that space as part of, as part of looking at some of the scheduling work that happens in this field. There is dual issue allowed, so there is superscalar, even like from a particular warp. So if you have 2 instructions, so let's say your iBuffer for each warp has 2 entries, and both of those entries are independent, and both of those entries go to different pipelines, like you have 1 tensor core instruction and 1 memory instruction that are both ready in the same cycle, you can dual issue that from the iBuffer from the same warp, as long as they're independent. Okay. Which is, superscalar, but it's statically scheduled superscalar. So you can't do it if there's dependencies between them. Right. So, you can issue to different, if there's actual space in the pipelines, you could potentially issue to more than 1 pipeline in 1 cycle, even from a different warp if the scheduler allows for it. And there's some partitioning that happens on modern machines that we'll talk about as we get into the microarchitecture a bit more to sort of have multiple warp schedulers. Okay, so each SM doesn't just have 1 issue warp scheduler anymore. They actually have 4. And they sort of spatially subdivide the thing and spatially subdivide the warps into 4 different subcores. So you can have more than 1 and issue more than 1 in any given cycle. Right, to avoid stalling the pipeline, you might keep the instruction in the iBuffer. So going back to your point, if you don't want to stall and you want it to perform a replay in place of a stall. So if there's a raw, right, if there's a dependency that you cannot handle, there's 2 ways to deal with it. One is just to stall, tell everyone not to do anything. Or the other way is to sort of do it. Like, for example, if you have a cache miss, you sort of send the thing down through the pipeline. When you hit the cache, you finally realize you have a miss, can't keep going. So then if you don't clear the iBuffer, you can go back to the iBuffer and say, replay this later. And then that replay could be triggered even when you could basically wait to replay the instruction until the thing comes back and is filled into the cache. Okay, instead of just stalling everything, you could implement it that way. And again, this is a design decision that, it's sort of a microarchitectural thing that different GPUs may choose to do in different ways. Okay. So what are some design challenges and issue and how have they sort of been dealt with? So now we have all of these multiple decoded instructions. We have multiple warps and potentially multiple instructions per warp. And we need to find out which ones can be issued without violating any dependencies. So in CPUs, as you know, there's out of order execution, there's reservation stations, there's register renaming that happens in the pipeline to try to, avoid dependencies and detect them. Can pick out a lot of ILP. GPUs don't do any of this. As I said, it's way too expensive. There is some minor register renaming that happens, but it's not register renaming in the sense of like CPU register renaming. There has to be register renaming because you can have more or less registers per warp based on how many registers the program needs, right? So sometimes every warp might need 256 registers. And then you would only have, let's say, 16 warps. But then sometimes every warp needs 128 registers. And then, you can have double the amount of warps. So that the mapping of the register to the particular warp is semi-programmable, but it's not sort of freely programmable like it is in a CPU where any architectural register could be any physical register, right? That's the flexibility you have in a CPU. In a GPU, it's more like a base offset thing that they have implemented. And again, that's kind of, low-level detail that we'll talk about a little bit more as we look at register files. But we still need to deal with potential hazards that we have in the pipeline without all of this out-of-order hardware. So you have to deal with read after write, write after write, and write after read if they exist. So how do we deal with some GPUs? So write after read hazards cannot exist in this pipeline, provided that the register file reads all happen in order. Okay, so if you do the thought exercise yourself, if I am issuing an order and my operand reads all happen in order, that means that the read order is specified and it is program order, which means that I cannot have this situation that is bad when there's a write after read, because what's happening on a write after read? What does that mean? What does it mean to have a write after read hazard? What's the bad thing that shows up? Yeah.
The write completes sooner than the read.
Right. So essentially, if I have, let's remind ourselves, right? So I've got an add, and I've got another add in this very simple case. And then I'm writing to R1, and I'm reading from R1 in this instruction. Okay, so this is this, let's call this R2 is the source, right? Whatever. So there's this, what do we call this? What's another word for this? It's a fancy word from 437 and 565 for this type of dependency. So if it's like this, R1 and then add R1, where you're producing a value and consuming it, what do we call this? A true dependence. Okay, this is a true dependence in the program. You cannot avoid this. There's actual data communication. What kind of communication do we sometimes call this? Sorry? Anti-dependence, right? Because there's no true communication here, right? You're not producing a value and then reading it. So what's happening is some weird out of order stuff in the pipeline is screwing up the program execution. Because what might happen here, so if you're doing out of order execution, right, then you could choose to issue this one first, out of order issue, and then issue this one second, which is a disaster. Because now this one is going to overwrite R1 before this one goes and reads from R1. And that causes a write after read hazard. In an out of order pipeline, you have to deal with this. In an in order pipeline, where you're guaranteed that the issue happens in order, and then that the register reads happen in order, which they do in this pipeline, that means that I have to issue this one first, which means I have to read its operand R1 first before I issue this one and before I even read its operands, which necessarily serializes this anti-dependence and completely removes WAR hazards from this pipeline. So I don't need any additional scoreboarding mechanism to track an anti-dependence because the nature of the issue engine guarantees that anti-dependence hazards don't show up. Okay? And this is generally true. This isn't just GPUs. If you have an any order pipeline, if you're doing like an embedded processor or something that's not doing any crazy out of order, you can guarantee register reads happen in order and issue happens in order, then you don't have war hazards in the pipeline, full stop. Make sense? Okay. So hopefully I've convinced you that the way this works, there are no hazards. You know, if you wanted to be super tricky and maybe have register reads happen out of order, which is one potential design point for GPUs, then you do have to deal with this. But the way that they're usually constructed, you don't have to. Read after write hazards and write after write hazards, however, are possible. Okay, like the true data dependence that I've listed here is, you know, you have to handle this in every processor because production and then consumption, and we have to make sure that the producer is done before the consumer actually reads the value. So that we have to deal with. And then we also have to deal with write after write hazards, also called what? What's the fancy name for the dependence that causes write after write hazards? Output hazard. Okay. Write after write is because I have an add, and then I have another add, and then they're both writing to R1. So the dependence looks like this. And if I issued these out of order, I basically wrote this one first and then wrote this one second, then the whole rest of the program is screwed because I have a stale value for R1 and that causes incorrect execution. That is possible. That is possible. Why? Why in the GPU, if I'm issuing in order and I'm reading operands in order, why is it possible that I can still have an output dependence cause a raw hazard or cause a WAW hazard? What about the pipeline might cause this? Loads can complete out of order. Yes, loads can complete out of order. Loads can cause this, but I could also have this without loads. What else could cause this besides two loads back to back, both writing to R1 and one hits into the later one hits in the cache and the earlier one doesn't? No takers. Nobody knows why this might happen. Yeah.
Maybe on, wait, is this an instruction on a cache list?
So forget caches. Let's say that my memory system is perfect and every load hits. Why would I have a WAW hazard on an output dependency? Yeah. Exactly. Out of order completion. Okay. Because the GPU pipeline is not just, basically you've got this issue engine. Okay. And then it issues into multiple parallel pipelines. So you've got your load store here. You've got your, integer here. You've got your FPU here. You've got your SFU here. So there's multiple pipelines that it can issue into, each of which has, by definition, usually a different depth, right? This is probably like a 2-stage pipe. This one is probably like a 20-stage pipe. This is like a 100-stage pipeline, which means that I have out of order completion, right? Because if I issue a division operation, it takes 20 cycles. And if I issue an integer operation, it takes 2 cycles. So even though I issue SFU first, I issue into this pipeline first, issue into this pipeline second, this one actually completes first and this one completes second, okay? Because the pipelines actually have differences. So out of order completion, and that's essentially what's happening with your load too, right? Is that they were completing out of order because one hit in the cache and one missed. But that occurs every time you have a multiple pipeline processor that they have different latencies, okay? Makes sense? And we have this in GPUs. And we have, of course, out of order load completion as well. Okay. Actually, it even says it on the slide. You guys didn't even read the slide. Since writes are not guaranteed to happen in order, output dependencies cause hazards. I guess, it's sort of a variant of what I just said. Okay, so the solution here is to deal with both. So we know that we don't have to worry about WAR, but we do have to worry about raw and WAW. So we need a scoreboard to basically implement this. And the scoreboard here is way simpler than the scoreboard that you would have studied in 565. The out of order scoreboard has to deal with out of order issue, has to make sure that the program order is correct. The in order scoreboard can be built very simply, basically a bit array with 1 bit for each register. And then all we're going to do is just check to see if the bit is not set, then the register has valid data. Essentially just a bit set that keeps track of in-flight writes. That's essentially what's going to have. 1 bit per register. If it's not set, then the register has good data. If the bit is set, then the register has stale data because we have an instruction in flight that is meant to overwrite that register. Okay. So that means there's something outstanding and going to change it. Okay. So the way that this works is sort of intuitive, hopefully. So you write to, so you have a function that looks like this. Your instruction is sort of represented abstractly as some function, right? So this is the opcode, right, of your instruction. It reads in RS and RT, which are the inputs, and then it writes to RD. When we perform the issue, we only perform the issue if this SD, this is scoreboard, okay? All this like alphabet soup here. This means scoreboard. Okay, so if the scoreboard at RS or the scoreboard at RT is set, then that means we have a raw hazard, because that means that the registers I want to read have a pending instruction in flight that wants to write to them, so I'm going to stall the pipeline. I'm not going to issue from this warp. It doesn't actually mean we stall the whole pipeline. It just means this warp is not ready. I cannot issue this instruction, so I can move to another warp. If RD is set, then I know I have an output dependence, because that means that I have an instruction in flight that was writing to the same destination register that I want to write to. To avoid confusion, we just stall, okay? Because we don't want to potentially create a WAW hazard. It's possible that if you're going to the same pipeline, they will be ordered, but there's extra complication to add that test case. So the simple thing to do is just wait for it to complete and then issue. If none of those things are true, then I can dispatch to the function unit. Okay, that's what dispatch to FN means. So go to the integer unit and do my add, and then set the corresponding scoreboard bit that says that this destination is now pending, because now I know that this instruction has been issued, it's in flight, and if anyone comes in after me and wants to read that particular register, I just go ahead and I don't issue them, because they have to wait until I'm done. Okay. Hopefully, sort of a weird way of describing a very simple algorithm, okay, that just implements an in-order scoreboard. They are allowed to complete out of order. Okay, so this still allows out of order completion. And when it does, you will update the GPR, let's say for general purpose register. That means the actual data itself, right? You go write the data itself into the register file at the index that corresponds to the destination register, and then you clear the bit in the scoreboard because now the write is done and dependent loads can carry forward. So this does not account in any way for forwarding. Okay, so if you did 437, right, forwarding is like the basic thing that you implement in pipelines to try to reduce stalling. Generally, GPU pipelines don't implement this because it's more complicated, and really all you're helping is ILP, right? Because you're just trying to get to the next instruction in a particular warp quicker. You're usually better off just switching to another warp if you have it and avoiding the overhead of routing 1024 bits backwards in a 20-stage vector pipeline, which is a huge amount of routing and switching for a minimal gain in ILP through forwarding. Okay, so there's no forwarding. They just wait for them to complete. And again, they can do this because they rely on multi-threading. Questions so far? Okay. All right, so if I tried to build this thing and I tried to do it in a really stupid way, okay, so let's say I had 64 warps, each of them has up to 128 vector registers per warp. It's actually 256, right? So every individual warp these days can access a maximum of 256 potential registers. That means that the scoreboard would need to have 8,000 bits to store, the state of 64 warps at, 128 registers each, which is a lot. So if you so that's a lot of storage just for a scoreboard for one bit. And then if I naively implemented it and all the warps that were waiting in the iBuffer had to continually check their dependencies and query every cycle, right? That's a huge amount of bandwidth on the scoreboard to try to check to see, am I ready to go now? Am I ready to go now? Am I ready to go now? Okay, which means you need this giant multi-ported scoreboard. These usually aren't an issue for single-threaded designs. So if you just built a sort of simple in-order scoreboard that you threw into an embedded processor, for example, you could just build this way because there's only one thread in flight. The problem here is that we have many, many threads in flight, and all of them may potentially want to check to see if they should execute this cycle, and you don't want to query the scoreboard every cycle from every thread to figure that out. You don't want a 256 port scoreboard, right? To have them all banging on the scoreboard to ask if it could go on any particular cycle. And so one solution is to read the scoreboard when the instructions write to the iBuffer, so not every cycle. This is sort of a straightforward optimization. So just check the scoreboard when you write to the iBuffer, and then you set your RBIT based on the state of the scoreboard when you entered the iBuffer. And then you have to then write to the scoreboard on write back. Okay, so you wait for the thing to be written on write back, and you'll update the iBuffer sort of at the same time. Okay, so instructions that are not ready in the iBuffer are generally not considered for the schedule. And there's actually a patent that describes this. So, we base this sort of relatively efficient scoreboarding on a patent that NVIDIA has published a long time ago that sort of says how to create a area efficient in-order scoreboard. I mentioned this, but then they basically threw all this away. So they did this for 2 decades. And then they threw it all away. I mentioned how they threw it away already. Does anyone remember, at least in the case of ALU operations? How do they pick up dependencies in ALU operations now? They don't use the scoreboard anymore. Yeah. They had delays inside the instructions themselves. Right. So the compiler is responsible for scheduling everything. And you can do that with GPUs because you can change the ISA, you can change the backend in every generation. You don't do this with x86 because it's are you really going to say that every add instruction takes 4 cycles and then you have to live with that for the rest of your life? Every processor you ever build takes 4 cycles to do the add? It would be in madness. But because GPUs do this intermediate translation, everything is in PTX, and then they can recompile it for the target architecture. They can say that, all right, the Maxwell had a 7-cycle delay on the FPU, and then the Volta had a 4-cycle delay on the FPU, and you don't have to recompile your code because in the back end, they sort of do this finalization step and then embed the actual delays into the binary itself, after after the fact, not in the binary, but in the actual instruction stream that the real machine sees, because they sort of have this intermediate step. Okay. So if you do this, you can reduce the scoreboard size. The other thing they do is actually only track 6 registers per warp. So instead of having 128, which is the possible maximum, you only track 6. And you do this with identifiers. But what that means is that your ILP is limited. That means that I can only track, I now have a structural hazard on my scoreboard. So if one warp wants to write to more than 6 registers at once in flight, it has to stall because it doesn't have space in the scoreboard to mark the dependency. And the I buffer basically is also limited, right? And the problem here also, there's also a problem of inputs, right? A lot of GPU instructions, particularly in the graphics world, actually have a lot of inputs. You can have up to 6 different inputs on some, texture-based operations. I think even more these days. So there are some very CISC instructions that need a lot of input operands. And like I said, when an instruction writes back, it clears the entry in the scoreboard and then clears all the dependency bits corresponding to the output register. And this is sort of what we claim the early GPUs, likely this is how they implemented the scoreboard. So here's an example to just sort of illustrate this, because I really did say a lot of words. So here's our warp instruction buffer, and we've got multiple entries in the instruction buffer. Here's a relatively simple piece of code. And then here is the scoreboard where we're tracking, 4 potential indices for each of the warps that are in flight. In this simple example, I'm going to assume there's only 2 warps. Okay. So how does this work? So the first instruction, the warp 0 will go and it will place the first instruction in the code in the instruction buffer. So the decoded instruction looks like this, at least, mnemonically. And then it has a field for each of the potential input registers that it has. Okay, they're all 0 right now because this is the very first instruction that's in flight, meaning that none of those input registers are waiting to be written to. Okay, I go into the scoreboard, and in the first index that I've got for warp 0, I tick off R7, okay, because that's the register that this first instruction wants to write to. Okay, this is how I'm going to fill out the I fields for all of the subsequent instructions that I issue from this warp. Okay, by basically saying R7 is going to be in flight. So then I go to the next instruction. Next instruction is a multiply. I take a look at the input operands for said instruction. It's R2 and R5. It's obviously independent of the load that I've got in flight. So I don't have any dependencies between any of, none of the inputs are actually dependent. So they're all 0. And then in my second index, I go in there and say that R6 is now also in flight. Okay. Then I have the last instruction, which is the add. So when the add goes and fills into the scoreboard or into the instruction buffer, I have to query this scoreboard with essentially a CAM, right? I have to go and say, is there R6 or R7 inside the scoreboard right now, or inside the scoreboard for warp 0 right now? And it will come back and tell me yes or no. And it will say that both of them are there. Okay, so this is a CAM, right? This is expensive, but the width of it is limited because we're limiting the amount of in-flight instructions we can have from every warp. So you can start to see how building a scoreboard gets expensive hardware-wise, right? And limits hardware-wise, which is why they sort of moved away from it, even in an order scoreboard in modern designs. So what happened here was the instruction queried the scoreboard. Our 6 and 7 were in there. The indices for 6 and 7 were in there. These are the first 2 operands, the input operands for this particular instruction. So I write 1s to both of those. Some time passes, okay? I also write R8 in here because now R8 is also in flight. And what will happen is some time will go by, and this is an example of out-of-order completion, okay? Because I issued all of these in order. And in this particular example, I'm going to assume that the multiply actually finishes first. The multiply will finish. It will basically do another deletion, right, from this small cam where R6 was. Or actually, wait, no, it doesn't actually have to cam this time. It doesn't cam this time because these indices are a one-to-one mapping to the entries in the I buffer. So it can just go to entry 1 and then clear it. So it only really has to cam when you issue a new instruction. So entry 1 will get cleared. Okay, so I will clear R6. And then anyone who is dependent on R6, which would be, the second instruction will we'll see that this happened, and then we'll clear the corresponding, dependency flag inside the instruction buffer when that instruction completed. And then we will, and so this whole time the ad has not yet been issued, right? The ad is still sitting in the iBuffer waiting to be issued. Then eventually the load will come back because let's say it was a load miss, which meant that the mole could finish quicker. So it'll go back and we'll see that R7 was, its index in here was 0. And so we'll clear that index and we'll check the dependent instructions. The dependent instruction here was the third one. And then we'll finally clear its bit. So then it will tell the issue scheduler, if all of these are 0, that's effectively like having the R flag set. And it says that you can then issue the instruction. Okay, so inserting into the iBuffer, you have to do this associative lookup. You have to check to see if there are any registers in flight that potentially violate these dependencies. Okay, questions on this? So again, this is just a sort of concrete implementation of the iBuffer. I went through this pretty fast. There's a video online for this. I do go through it a bit slower if you want to go take a look. I think it does a fairly good job also of explaining this. Other questions? All right. Right. And so like I alluded to, now everything is actually managed through the ISA. A lot of the dependencies that they can pick out statically as of Kepler, which is 2012, I think, 2013. They got rid of a lot of the need for a big scoreboard because they encode all these dependencies in these crazy control flow codes that are inside the instruction stream itself. Okay. Questions on any of this? All right, so we're going to move to the last sort of microarchitecture piece that we'll study in a baseline GPU, which is reading operands. And the way that this will work is that we'll look at the final scheduler that's inside this pipeline. Okay, make it one step more realistic versus what a real GPU looks like. So we talked about fetch scheduler. Everything I just talked about in the last 40 minutes is about the issue scheduler, but we sort of were assuming that we could do huge amounts of read throughput in the register file every single cycle, especially if we were issuing to all of these pipelines, right? Like I said, you could issue to more than one pipeline. Every time you issue, you need to read a whole bunch of registers. Those registers are wide because they're warp registers. They're 1024 bits. If your SIMD width is 32, and they're all float registers, so that's 1024 bits. That's huge. And the register file capacity is also huge because you need a lot of registers to keep a lot of context on these cores to make sure that you can have huge multi-threading. So you have these sort of two competing demands: the need for a giant register file and the need for a high bandwidth register file. If your RF doesn't have enough bandwidth, your whole pipeline is screwed, right? This is, more so than the L1 cache, this is the thing that you need to make sure is doing good work every cycle, or else your units aren't busy. They're not being fed. So all the context is kept resident in the register file. We're not swapping things out generally. So if a warp gets scheduled there, it consumes those registers and it lives there the entire time that kernel runs, and it doesn't get freed until that warp is done, or until that thread block is done. Right, lives there the whole time the thread block is, or at least the warp is executing. In modern GPUs, this is actually bigger now. We're talking more like close to a megabyte worth of register file on each core, which is huge because that's per core. And then you consider you have 100-something cores, right? You have tens to hundreds of megabytes worth of register file on a GPU. And if you think about the last level cache, it's only going to be like 20 megabytes, 30 megabytes or something, right? So it's actually far bigger in the aggregate than the size of the last level cache, which is completely inverted from how you think about normal CPU architectures, right? Like the register file is tiniest, and then the sort of L1 cache is bigger, the L2 cache is bigger, and the LLC is bigger. In the GPU, the register file as sort of a raw capacity perspective is much bigger than the other levels of the on-chip memory hierarchy. So it's huge, and you need to read multiple values from the register file every cycle to maintain throughput. So for example, a fused multiply add instruction, which is the instruction that you need if you're not using tensor cores, and it's sort of also what tensor cores need to do, but you need a higher throughput. It takes 4 operands, and so you need 4 read ports from this giant register file in order to satisfy issuing this instruction in one cycle. And if you don't issue a new instruction every cycle, then you are by definition not using your pipeline. right? Like if it takes me 2 cycles to clear, the average, if it always takes me 2 cycles to clear my register read stage, and it's not pipelined, I'm not like ending the register read stage with a new instruction every 2 cycles, then I'm screwed, right? Because my pipeline is going to be starved. So I need to make sure that I can get stuff through this pipeline such that I can feed each of the downstream, or through the register read such that I can feed each of the downstream pipelines at whatever rate it is that they need, which is huge. Right, and you can dual issue to multiple pipelines. You need more ports, big ported structures, bad for area and energy, as people sort of know. So what is a naive way to potentially implement register files on GPUs? Well, we know we don't want a big multi-ported structure, so we can't do that. So that's out of the question. So one way to implement this is with banking. Okay, just like we did with the shared memory, we're going to take that big storage structure and we're going to split it into separate, distinct storage structures. Okay. So now I can just have a single port register file, and I can have 4 banks in this particular. This is what we call a straw man. Has anyone heard the term straw man before? What does a straw man mean? Whoa, this is deeper than I had. Perfect philosophy. Okay, go on.
If I want to refute the claim you make,
Yeah.
instead of using the claim you make, I use a weaker version of your claim, and then I refute that version, and then I say I actually refuted your version.
Oh man, that is a pretty that's a deep move. Like I was, so you're intentionally obfuscating somebody's position to make it easy to refute.
Yeah.
Okay. It's sort of how I'm doing this. I think of it like a straw man, like a straw man. You know what? You know what the sort of impetus of it is, right?
Yeah.
It's like, what is it? This is Indiana. What is a straw man? A scarecrow, right? Which is like a man farmers put in fields that's made out of straw to like keep birds away, because birds, if they're really stupid, if there's a person standing there, they won't come around. So, but the birds still come, right? They don't really work. It's part of the reason it's called the straw man. So the straw man microarchitecture, I'm not intentionally taking someone's argument and making it worse. This is just like, it's something I know I can beat, right? It's like, this is a simple way to do it. It's not going to work super well, but it's a place to start. Okay, this is our straw man. Our absolute straw man is just a huge multi-ported thing, which of course you can't build. So I'm going to try to get around ports by doing that. Okay. So the way that I would build this straw man microarchitecture, and I'll cover this in the last couple minutes here, and then we'll go into more detail with it on Thursday, is this fundamentally is the operand read stage. Okay, so that means that after decode. Okay, after I've decoded the instruction, I enter register read. Okay, this is post-issue, means I can issue the instruction. So I have a pipeline register in my microarchitecture that holds the instruction itself. Okay, that encodes the registers that I need to read and write to, encodes the opcode, tells me what warp I am, so that way the rest of the pipeline knows what to do with the instruction as it carries through. So that's the input to this thing. Okay. Then the input to this thing has access to all of these different banks. And then in any given cycle, I take a look at what registers I'm reading from and what registers I'm writing to in this instruction. Okay, so this particular instruction is reading from R5, okay, and R1. That's what this says. Sorry that the black thing sort of covered it, but that's what it says. So it reads from R5 and R1. If R5 and R1 are in different banks, then I can nominally read them both out in the same cycle. Okay. If they aren't, then I have to serialize on the bank. Okay, so there has to be some layout. And so this is true. And the banking part is not a straw man. This is how they implement register files. But what they do around the banking is a little bit more nuanced, which is something called an operand collector that we'll get into next class. But there has to be an assumed layout. Okay, so that means that every warp register pair has to live in one of these 4 banks. Okay, so for example, warp 0, so this is warp 0, and it wants to read register 5. So warp 0, register 5, do I have it listed here? Yeah, here it is. Warp 0, register 5, in this layout lives in bank 1, okay? And then warp 0, register 1, warp 0, register 1, do I have it in here? Yeah, warp 0, register 1 also lives in bank 1. Okay, so in this particular example, both of the registers that I want to read from live in the same bank. Okay, which means that I'll have to serialize. So it's going to take me 2 cycles to clear my register read stage instead of 1. And the way that this works, right, is that at the end of the day, we need to fill another pipeline register that sits in between register read stage and your execution stage, right? That then sort of has the SIMD units that do the math. Now, if I was reading from 2 different banks, I have this crossbar. So for those of you who don't know what a crossbar is, just think of it as an interconnect network that can connect all inputs to all outputs. Okay. So if I had a good access where I wanted to read from bank 0 and bank 1 and then write to the 2, so each of these are vector registers that I'm reading from. Okay. So let me just explain that because some people do get confused. When I read from warp 0 R1, I'm reading out all 32 lanes. Okay, there's no weird, like some lanes are in some bank, some lanes are in another bank. We don't do that. Okay, when you read from a bank, you read out the full width of the register. So we're reading out the whole 32 lanes from bank 0, and then we would store that in a pipeline register that would basically correspond to the first input operand. Okay, and then if it was in another bank in that same cycle, I would read that out into another pipeline register that stores the 1024 bits that correspond to the R1 in this example. And then I would have R1 and R2 sitting in the pipeline register ready to go for the next cycle at the SIMD units. Okay, that's how this would work if there was no bank conflicts. But because there's a bank conflict, I have to schedule it over 2 cycles, which means that I basically end up with a complete serialization of my pipeline. Because I can't clear, if it takes me 2 cycles to clear the register read stage, unless I'm running this at half the frequency, then I have a bubble naturally, right? And you do not want bubbles in GPU pipelines. You want to try to fill them as much as possible. So we want to create a situation where we never have to be not issuing to the pipeline in the ideal case, okay? And you can do that you can do this with clever swizzling of these numbers. So swizzling is this, kind of funky word that really means like rearranging things, like reordering things. So if I was clever about what bank corresponded to which register, and I told the compiler what bank corresponded to which register, the compiler could do a better job of doing register allocations such that every individual instruction does not have bank conflicts. Okay. But there's an added wrinkle here because I actually will have more than one instruction in flight potentially in GPUs. And I won't always be able to force the compiler to sort of do this swizzling in a perfect manner. So, the fact that you need to bank this structure causes this potential bottleneck. And we're going to get around it by essentially allowing more than one instruction to be in the register read stage at any given cycle, as opposed to just one at a time. And then we're going to buffer all of our operands into these things called operand collectors, such that we can sort of overlap, right? So let's say that warp 0 has a bank conflict, and it can read from bank 0, but then warp 1 doesn't have a bank conflict, or it reads from warp 1, and then warp 2 reads from bank 3, and then warp 3 reads from bank 4. If every cycle we're reading out at maximum throughput across all of the warps that are in flight, then in the aggregate, we're going to keep the back end busy, right? If we match the bandwidths. So that's essentially the idea behind the operand collector. Don't serialize things in the register read such that there's only ever one instruction, potentially reading. We're going to allow the read to actually there's going to be a new scheduler in here that's going to decide who gets to read registers on any given cycle between all of the warps that are in flight. And then we're going to buffer all the operands in these things called operand collectors. Okay. That's the 10,000 foot view. We'll come back and study this in a lot more detail next class. Any questions before I let you go 5 minutes late? All right, I'm done. I will see you guys on Thursday. No quiz? You guys did okay. Who actually read the paper? In all honesty, all of you? Really, most of you? Okay, all right. It's not really a paper, right? That was it's like a tech report. That was the easiest paper you should have ever had to read. All right, I'll see you all on Thursday.